Hi, in this video, we want to take a look at ANOVA, specifically the assumptions and diagnostics for running an analysis of variance test. All right, so remember that when we're running ANOVA, we have subgroups and in our data, and we want to see, do we have different averages within different subgroups? All right, and so, how we generally approach this is by using ANOVA. Other ways that we can do this is do pairwise t-tests. We can also do it visually. There's lots of ways that we can approach this, but the standard in scientific research is to use ANOVA. All right, so what we're going to do, we're going to go over the assumptions for ANOVA. We're going to go over diagnostics to check to see if our assumptions are reasonable. Then I'm going to go over some visualizations that we can use to support our conclusion when we're running ANOVA and we're presenting to our stakeholders, or to use actually as a way of reaching a conclusion without using ANOVA at all. If I have an audience that doesn't have a stronger statistics background, I can use these techniques to show them the conclusion that I'm reaching without having to run through a hypothesis test, p-values, and stuff like that. Because if they don't have the background for statistics, I'll just be speaking gibberish to them. All right, so let's go over the assumptions of ANOVA. All right, so here I'm just talking about, most basic version of ANOVA. If I have a more advanced version of ANOVA, there's going to be additional assumptions going on. So specifically, if we're talking about, higher dimensions, more independent variables, or if we're talking about nested or, a mixture of situations, then our assumptions are going to have to be more expansive. But here, I'm just going to talk about the ones that apply every single time that we run ANOVA. All right, so when we use ANOVA to analyze the difference among groups in terms of the average using a sample, here are the key assumptions that we have to rely on. First one is independence. Second one is normality. The third one is homoscedasticity, that is equal variances. All right, the one that is absolutely the most important is independence. And then I would say, in my judgment, the second most important is homoscedasticity, equal variance. And in my opinion, normality is the least important of these three. It's still important, but it doesn't have to be strictly normal. It just kind of has to look normal-ish, like a bell curve, kind of, when we run ANOVA. All right, so independence for each sample is independently drawn and the samples are mutually independent. In practice, this means that the data should be collected using independent random sampling if we can achieve that. Now, for normality, the residuals or errors of the model need to be normally distributed. This does not assume that the variable itself is normally distributed, just the errors. That's important. Because if I have different subgroups, let's say I have subgroup here, and they have very, very, very extreme different values for their central tendencies, for their means, then the distributions of points here and the points here won't even overlap when I start doing my histograms, when I start, looking at, box plots or density estimation. And so I will get two modes and in the distribution, and with two modes, that can't be normal. Now, for equal variances, the variance among the groups should be approximately equal. This is also known as the assumption of homogeneity of variances. So let's go run through some examples. I'm going to run through an example. I'm going to use the same model every single time for the examples that I'm going to be going through, and because I want to be consistent. And so we're going to beat this model to death. We're going to go overboard with this. So here I have the MT cars dataset. This is a classic dataset that comes in base R. We're saying that horsepower has different averages across cylinders, carburetors, and we have a main effect for each, and we have an interaction effect for each, between the two. And we're running analysis of variance, and then the ANOVA, or the summary function, prints the output. All right, so typically when you look at blog posts and videos, when people use empty cars, they go off of miles per gallon. I like fast cars, so I chose horsepower. All right, so here we can see the main effect of cylinders is statistically significant, very small p-value. Carburetors, once again, we get a small p-value, statistically significant, and the interaction is statistically significant. So we'll keep that in mind as we look at our visualizations and our diagnostics as we proceed through this. Now, how do we check our assumptions? Well, we're going to run diagnostics, and we want to check to make sure that things seem like they're going the way they should. Now, the first one, the test for independence, really, like there's ways that we can check for like lack of autocorrelation, but it's hard to truly nail this down. And so really, this is more about having a good solid study design than something that we can really test for. Autocorrelation, or just visualizing the values in terms of what I see over time. Yeah, sequentially as I collected my data, that's something I could do if that's applicable, if that makes sense. But really, this is more about just making sure I'm collecting my data in a solid manner in the first place. And we want to make sure that we have independence between our observations all the way through. Now, our test for normality, there's a whole bunch of different tests that we could use. We could use Shapiro-Wilks, and we could use Kolmogorov-Smirnov tests. Here, Shapiro-Wilks is specifically designed for the normal distribution, and it's the most likely to reject the null hypothesis of the ones that I know of. And Kolmogorov-Smirnov test, this is generic, and it works for any relative distribution we want to check against. This one is not as sensitive to rejecting the null hypothesis. So what we have to do, we have to take our data and identify that we want the normal distribution in this test. We also use visual methods such as QQ plots, or we could also check things like histograms, and we could check box plots also, just to visually look at the distributions. Test for homoscedasticity. We could use Levine's test or Bartlett's test for this. Visual inspection of the residuals can also provide insights. The residual plots should show equal variance around the zero line. So when I plot the residuals, I want to see equal variability along the zero line. And analysis of the residuals. Residuals can be further analyzed using plots. And so, one thing that we would like to look at is relative to each main effect, plot, main effect and plot the residual by the main effect. That would be used. We can also plot the residuals versus the fitted values. And this one in particular can be used to reveal nonlinear patterns or unequal variances and outliers. It's important to note that ANOVA is robust to minor violations of these assumptions, particularly when sample sizes are equal across groups. When sample sizes are unequal, more stringent adherence to assumptions is typically required for the results to be reliable. So when we say unequal sizes, typically what we want to do, when I have unequal size, I want to think of my power and I want to think of my power and my robustness in terms of the smallest sample size among my groups. And then, think of it that way. Even if like other groups have a large concentration, that small group there, it's possible that we can end up having problems because it's so sensitive to what we end up getting. Now, test for normality. Here we're going to run through an example. So we're going to use a QQ plot and the Shapiro-Wilks test. Shapiro-Wilks is going to be prone to rejecting the null hypothesis compared to the Kolmogorov-Smirnov test. A QQ plot, in this plot, what we want to do, we want to see the data looking like a straight line when I do this special type of plot. This type of plot uses the the hypothesized probability distribution to figure out what the position of each dot should be. All right, so here in this model, we have that horsepower is depending on cylinders, carburetors, and the interaction between those two. All right, so here I'm fitting the same model I did before. Each code chunk I built up stands alone by itself, by the way. If you need to copy, you won't have to copy up earlier in it. So now here I'm grabbing the residuals, and I'm going to go ahead and plot using a QQ plot. So in the ggplot2 package, it's stat_QQ to plot this. Most people use base R for a QQ plot. Here we're using ggplot to do it. And to have a reference line, we're going to do stat QQ line on here. And so let's take a look at our plot. All right, so here I can see that there's a little bit of deviation here. This one is kind of far off to the left. It's a relatively small sample size. I am leaning towards it not being normally distributed at this point. You'll notice that these points, as I go from left to right, the y coordinate is always increasing. And if I have a normal distribution, ideally, theoretically, if every single individual value behaved as expected, we will get a straight line here. All right, so now the Shapiro-Wilks test, we can see that we reject the null hypothesis. We conclude that it's not actually normally distributed. Now, that might be okay. Shapiro-Wilks is very prone to rejecting the null hypothesis. And so what I'd want to do is, check box plots, check histograms at this point. I didn't do it here. I didn't want to make this too long of a video, and see, does it look reasonable to use the normality, use ANOVA. Now, remember that we don't have to have normality, it just has to be close to it. And Shapiro-Wilks is very prone to rejecting the null hypothesis. Practically speaking, if I have a huge data set, Shapiro-Wilks is going to reject the null and conclude that we do not have normal, by the way. All right, so in the Shapiro-Wilks test, the null hypothesis is that the data is from a normal distribution. So here, in our case, the null hypothesis is that the residuals are from a normal distribution. If the p-value is less than our significance level, and let's go with 0.05, we reject the null hypothesis and conclude that the residuals are not normally distributed. If the p-values are larger than our significance level, we do not have enough evidence to reject the null hypothesis, and we would conclude that our data is coming from a normal distribution. Now let's look at tests for homoscedasticity. All right, so what we want to do here is we want to decide, do I have constant variance across different subgroups? All right. And so here I'm going to go ahead and take my ANOVA model, I build it. I'm going to grab the residuals. I'm going to grab the fitted values, and then I'm going to plot them in ggplot. And here I'm plotting the points, and I'm going to go ahead and put a smoothing curve onto there. So now what I'm doing is I'm taking my fitted values and I'm putting those along the x-axis, and I'm putting my residual values, the error in the model, the difference between observed and modeled values, and putting that on the y-axis. And then I take a look. All right, what I want to see is, so here what I'm trying to do, I'm trying to determine, does it look like I have constant variance? And typically, most situations will have like a shape coming out. Now, in this particular case, honestly, we have such little data, it's hard for me to conclude something. With this small of data, any conclusion that you want to draw in your mind, pick up a point and move it in any one point. If you can find a point and move it to another spot that contradicts your conclusion, you don't have a reliable conclusion going on. And so here I'm looking, and possibly I might have more variance here. Possibly I might have more variance here. It could also be an artifact of just having just more frequent values at this particular level. Here I don't have a strong opinion. Honestly, either way, because of the lack of the data, but I would lean towards saying we have constant variance, but not by much. When I have more data points, it's easier to actually like pick out what's going on. So now we can run a test. So here is the test to run using the LM test package. And if I just drop the model into the test from the LM test package, I can see that we failed to reject the null hypothesis. We conclude that we have constant variance. Now, we can also analyze the residuals. So something that I can do is I can plot the residuals by main effects, and I can plot the residual. And when I plot them, I can do it as a box plot, B-swarm plot, or a histogram if I want to start digging into it. Here, I'm just going to actually repeat the same one because this is the most important plot to be looking at to emphasize. Now here, when I do this analysis, so previously I was only interested in constant variance. Now, something I want to do on this step, when I have this visualization, and I wouldn't make two of them, I would just do it at the same time in real life, I would be checking for a shape. So if I saw like a horn shape coming out, or a triangular region, or something like that with a pattern of my dots, then I know that there's something going on. There is some problems in my modeling, and I might need to run a transformation on my target variable, or I could possibly, start, changing up the model, or I could potentially use a non-parametric approach. I have to basically wade through it and figure out what's the best choice. Now, if I have a time aspect in my data, I can, plot my values as a time series. So if there was a sequential collection of my data, then I could record the time and put that in here. That's not appropriate for MT-CARS data set, but I could do that. And, once I have time series data, I can run to see, do I have autoregression? Do I have a moving average model? If I have an autoregressive model, then clearly I do not have independence. Also, when we look at this fitted versus residual plot, we can, check to see if there's outliers that are significantly far away. Here, the more extreme values, I don't consider outliers. Just I feel like I don't have enough data to conclude that it's an outlier yet. And so an outlier, remember, we're taking sample averages. Outliers are going to pull averages away from the rest of the data. And so they would have undue effect, and they can throw off my model. I might want to filter out outliers. All right, so now I want to talk about visualizing the ANOVA test without actually running the ANOVA test. And this is one, my opinion, before you run ANOVA, you should do these types of visualizations. And so we can call these one-way plots, first and foremost. So here's a one-way plot of cylinder and the individual values. And this is called a B-swarm plot. When I have more data points, what will end up happening is ggplot will start putting the dots in their correct vertical position by their categorical predictor variable position. And you can see, like here, we've got close values, and they start like clumping up, and they start looking like a beehive when you have a lot of data points. And so here we can see that visually, my central tendency is around here. Visually, my central tendency is around here, which is greater than over here. And visually, my central tendency is here. So this is a good way to convince people that we have, different average locations. So the reason why I like B-swarm plots is that really I can show these to anybody. I say, when I was working in education, I said each dot represents one student. And so since I see a difference in these positions, I know that there's a difference between these subpopulations. And so each individual point is a record, an observation, whatever level of measurement I have. And people understand that very well. B-swarm plots work very well when I have an audience that's not comfortable with box plots or other visualizations. Each point is a record, really resonates with people a lot. So I like it a lot. Disadvantage is that B-swarm plots don't work well when I have a lot of data. It's hard to make sure that things don't overlap with each other, that if I had a lot of points, you can imagine the blue and green having so many that they overlap and get on top of each other. It takes a long time to compute to get the right position so that the dots aren't overlapping. But overall, I really like this. When I have a lot more data points, it'll start looking like the empirical distribution also. So now let's take it, same plot, but in terms of carburetors. And so we can see I have my carburetors along the horizontal axis, and I have horsepower on the vertical axis. And we can visually see that it looks like there is an increasing aspect. It's harder to spot here because we have such sparse data points for each level. And now if I want to do this for carburetors and cylinders at the same time, I can do that by using the interaction function to create a new column of data. I call it cylinders, carburetors, right? And so here, you could also use the paste function to achieve this. We can plot it. Now, the main effect for cylinders appears to be bigger when I ran the initial hypothesis test. So I colored by cylinders, and you can see here's all my reds. Here's my greens, except for there's a blue in between. And then if I switch these two in position, I would see that I would have red, green, and blue perfectly lined up. This further supports that cylinders are definitely important for the visualization. Now for the interaction, the greens are pretty close to each other in vertical position. These I really can't see much of a difference, but here when I look at the blues, it looks like to me that the interactions is really only coming into effect when we have 8 cylinders, which is an interesting observation to pull out so that I'd be able to talk about that. Now, it's still a light data set. I want to approach that conclusion cautiously, but tentatively, I could go to subject matter experts and say, it looks like to me that there is an interaction effect when the cylinders are only 4 or 6, but when we have 8 cylinders, there's more. And honestly, that makes sense to me from my time working on cars. So, which wasn't very long, but I did for a little bit. Now for box plots, a box plot is a 5-number summary. Now, people do not like box plots. I recommend you don't show these to the majority of audiences. They're good for scientific papers. They're good for stakeholders who have stronger math and statistics background, but people just inherently don't like box plots. In the state of Florida, box plots are actually part of the 7th grade curriculum in mathematics. So we should be more comfortable with them than we are, but it is what it is. So I find my best advice to you is don't use box plots. Now, honestly, we have such a light data set, I don't really trust these box plots that much. The B-swarm for this case is a better choice. When I'm looking at differences, what I really want to see, I want to see the box in the box plots. For the purpose of ANOVA, I want to see that they're vertically in different positions. Like one is higher than the other, and there's no overlap. And so here I see that this box is lower than this box, lower than this box. This supports the hypothesis that there is a difference in horsepower by cylinders. Okay. Now we can also analyze the variance about the median. So if I see asymmetrical in the box, that supports the conclusion that we do not have constant variance across subgroups. And here we go by carburetors. And so we can see that it looks like there's a bit of a difference, but carburetors, it's not as strong of a difference as it is for cylinders because I have overlapping boxes. When I have overlapping boxes like this, that leads me to believe that if there is an effect, it's not as strong of an effect. With a large enough sample size, this amount of overlap would be enough for me to conclude that there's a difference. Specifically, I want to see, when I have a larger data set, I want to see that the medians do not cut into each other's boxes horizontally. And now we can also do the plot with the interactions. And so once again, we see our red, we see our green, and then we have these blue ones over here. This one is a green and these two are blue. So this further supports the conclusion of different averages. And we can see that, we see more of a difference in the blue in terms of interaction. And so this supports that conclusion I reached earlier that the cylinder carburetor interaction really doesn't manifest itself until we see 8 cylinders. Now, the next one is the violin plots. Violin plots do the same thing that we've been doing, but they work to give us the empirical distribution in this manner. So here, this is estimating the empirical distribution of each of these. You kind of have to turn your head to see it the way you would with other plots. And this, can visually give us a way of analyzing it. I find that people without a strong statistics background don't like this. Even people who have worked with data a lot don't like these. Usually you want to do these when you present to people who work with empirical distributions frequently. If they're not comfortable fitting a distribution based off of data, then you probably don't want to show this one because that's what a violin plot is doing, really. So that's main effect for cylinders. Here is main effect for carburetors. And honestly, I'm not really seeing a whole heck of a lot. These violin plots don't tell me a lot because it's such a small data sets. And then we basically see a repeat of what we saw with the interaction. All right, well, that's all I've got for you. Life is short. Do math.